White dwarf stars might be harboring some of the most enduring habitable regions in the galaxy, as new research suggests. A study by Manuel Barrientos and his team at the University of Oklahoma reveals that between 0.6% and 2.5% of white dwarfs in our solar neighborhood experience dramatic cooling delays, potentially extending habitable zones for billions of years. The key to this phenomenon lies in neon-22, the most abundant element in white dwarfs after carbon and oxygen. When white dwarfs contain at least 2.5% neon-22 by mass, they undergo a process called distillation as their cores crystallize. This occurs because solid crystals become depleted in neon-22 compared to the surrounding liquid, making them lighter and causing them to float upward, where they melt. This creates an astronomical equivalent of a lava lamp, releasing vast amounts of gravitational energy that pauses the white dwarf's cooling for up to 10 billion years. Neon-22 forms during a star's lifetime through a well-understood process. During the helium burning stage, nitrogen-14 produced by the CNO cycle transforms into neon-22. Stars with higher metallicity, carbon, nitrogen, and oxygen abundances produce more neon-22 in their white dwarf descendants. To test this theory, the research team analyzed 4,000 stars from the Hypatia catalog, using the MESA stellar evolution code to model neon-22 production in white dwarf remnants. Their predictions align with Gaia satellite observations, which detected an unusual clustering of white dwarfs on the Q branch in brightness diagrams. About 6% of massive white dwarfs appear to have paused their cooling for 10 billion years, creating a cosmic traffic jam. Additional evidence comes from stellar velocities. Stars in the Q branch move faster than expected for their apparent age, suggesting they are actually much older than their brightness implies. Evidence of the cooling delay. What makes this discovery intriguing is its galactic pattern. Distilled white dwarfs are most common near the galactic center, 7.6% within 2 kiloparsecs, and decline toward the outer disk, 1.0% at 8 to 10 kiloparsecs. This gradient reflects the galaxy's underlying chemistry, with metal-rich stars producing neon-enhanced white dwarfs more prevalent in the inner regions. The findings suggest that long-lived habitable zones around white dwarfs should be most common in the Milky Way's inner disk. These implications challenge traditional views of white dwarfs as dead ends, proposing they may be stable, long-term habitats for life. With billions of white dwarfs in our galaxy alone, and a significant fraction potentially hosting extended habitable zones, the universe might offer far more opportunities for life than we've imagined, hidden among the galaxy's most common stellar remnants. However, some surveys have detected suspiciously high numbers of massive white dwarfs in the solar neighborhood, which contradicts the new model. The team suggests this overabundance may stem from observational bias. Distilled white dwarfs remain more luminous for extended periods, making them preferentially detectable in magnitude-limited surveys, leading to their overrepresentation. This research shifts our understanding of where life might exist, redefining white dwarfs as potential stable, long-term habitable environments. With billions of such stars in our galaxy, and a significant fraction possibly hosting extended habitable zones, the universe may hold far more life-supporting possibilities than we previously thought. The findings are published on arXiv, https arXiv.org/abs2508-12600, and more information is available at https thys.org/news/2025 White Dwarf Stars, Common Habitable HTML. This document is subject to copyright. Fair dealing for private study or research is permitted, but reproduction without permission is prohibited. The content is provided for informational purposes only